And you guys know that in the reading, the very first NMSI, the very first one that you guys read, there was the very last page was all on.
Good morning. Attention students taking the ACT Work Keys assessment. Please report to the auditorium at this time. Teachers, please check your email to confirm if you have students who need to report to the auditorium. Thank you.
All right, so 2 things I just want to talk about here are that and this is actually from the AP Chemistry curriculum guide. Like, you can always go read that in your free time. It's like 350 pages, but you can do it in snippets, right? So do you know that the activation energy of a single elementary step is what it's lowering? Okay, so that's one option what a catalyst will do. I have a picture of that in just a second. And 2, another alternative for a catalyst is that it could technically change the entire mechanism. It could change one of the elementary steps to be a different elementary step, forming a new intermediate, which hopefully that new intermediate also had a lower activation energy alongside of it. But it either changes the activation energy of a single elementary step, or it makes a totally new mechanism to create a new intermediate. Okay, so those are 2 different things that a catalyst can do. And there's one picture here, and this is a reaction diagram. Is this endo or exo? Exo. So we could definitely just show beginning and end the same, but the catalyst would just impact the activation energy of this single elementary step by lowering the activation energy. Or it could do this. So what has it done? So it has created a secondary elementary step, so it has changed the activation energy, and it's changed the mechanism, right? Because there's now, instead of being 1 elementary step overall, there are 2 elementary steps, so therefore it has changed the mechanism, creating a different intermediate. Cool? Okay, so it's pretty simple. It's something that maybe you've heard of before, like, changing the pathway, changing the energy barrier. That's another way of stating it, but it all just means it speeds up the reaction by changing the mechanism in some way or form. These are the 2 types, homogeneous and heterogeneous catalysts, that you should be able to classify. It's all based on state of matter, though. So if all the catalysts, the reactants, and the products are all the same state of matter, what's the prefix for same? Homo, so homogeneous here. So you've got the products, the reactants, and then the catalyst. They're all in the same phase. So you see they're all spread out here. What phase do you think that is? Gaseous, probably. And then in the other scenario, you have a surface catalyst, and the surface is like platinum or zinc. Some other good catalyst. Nickel, copper. There's a lot of metals that are surface catalysts. So like a catalytic converter uses platinum. So this would be a solid, and the rest of the reactants products would be probably gases. So that would be an example of a heterogeneous. So hetero means different, so different states of matter. And so this is an example of like the nitrogen monoxide and maybe the carbon monoxide that come out of your exhaust, pass over the platinum, get changed to cleaner gases that would be put out through your exhaust. The last kind of catalyst that we kind of talk about is specific to like biochemistry, so it's our the biology inside of us. We have enzymes that are serving as catalysts, and this is just an example. Who remembers this from biology? We know the catalysts bind, right, with the binding site. So this right here is kind of like called the active site or the binding site. So the catalyst, which is the enzyme, bonds to something, and then so actually this is the compound. Reactants come into the catalyst at its binding site. This reactant is then immediately changed to 2 different products. So that's what's happening here. So the whole nature of catalysts are that they're speeding up reaction, they're helping a reaction occur by nature of pulling things together. Okay? So the reading that is at the very last page of your NMSI, the first one you guys did, looks like this. I just pulled the things that I thought were important. We already did talk about some of this, but you maybe haven't written it down yet, but you probably saw this in your multiple choice. Catalysts are not consumed. Okay, so they're still with us from the beginning to the end. We've seen that from our mechanisms and how we cancel them out. The 3 classes of catalysts are acid-base catalysis. Where have we seen that? Where have we seen like acids helping speed up a reaction? Redox, right? So when we did our potassium permanganate titration with hydrogen peroxide, what do we add to that to speed up the process? Say again? Sulfuric acid, and then CJ spilled a had to neutralize it for a good like 15 minutes. But yeah, so acid-base catalysis would be like a redox reaction. So we are balancing in acid and balancing in base. That's the same scenario. Surface catalysis would be the example that I just used, which is what? Say again? Like exhaust, so like a catalytic converter has like a metal surface where the reactants will bond to or take a place to meet at and then react. And then enzyme catalysis. Okay, so those are our 3 big categories. I think we got the rest of this. We know that we can show the reverse reaction being catalyzed as well. So just like we can decrease the activation energy in the forward direction, it also would decrease the activation energy in the reverse reaction. So it'd be small. Oops. The red one here is the forward reaction EA, and the green one would be the reverse reaction EA, just because it can catalyze both sides, both directions. And these just give you further examples of homogeneous and heterogeneous, so you guys can read up on that for some more examples if you need to, okay? Give me a thumbs up, I can move on. Okay. So I just want to make sure I covered catalysts with you before moving on to checking, and these are just really good examples. So these are big misconceptions. So I would like for you to read them first, then write down what you need to. These are just misconceptions that are kind of common through kinetics and this topic. So after you finish reading the first, what's up here, write down what you need to move on. Okay, so we know that the intermediate, whenever you're drawing your reaction diagrams, draw it in the air for me, and where does the intermediate occur? Okay, so it occurs in the lull, right? It's not at the peak, it occurs down here. So before the secondary step is going to occur. So what is the peak called? Transition state or activated complex. And then, so this is called the transition state or the activated complex. And if I have a secondary reaction or a second elementary step, where's the intermediate? At the little lull down here. So this is the intermediate. And then we have another transition state or activated complex, and then we can have our final products down here. We know how to determine, between a series of elementary steps. One of them is going to be the slow step. The slow step takes the longest, so it's going to have the highest peak to achieve, which would be the highest activation energy. Smallest k technically means that the reaction is what? Fast or slow? Slow. Okay, so k value is our rate rate constant. That's when we're also reflecting the rate of the reaction, and we're not. We are suggesting mechanisms based on data that we collect in the lab or observations that are made about that reaction. We're not proving the mechanism. That's what we have to always check based on the criteria. What are the 2 criteria that we need to determine are correct or true before we can propose a mechanism? BCE matches. Say again? Raise your hand for me. Help me out here. Christian, what you got? Give me one criteria for how we say a mechanism is possible. Something with the coefficients. Let me pick up from there. William? Okay, so some elementary steps matches the overall BCE. Okay, and then Cassie? Okay, so we're going to add one more to that. The slow step matches the, anybody? There's a word I want you to use. So you could say coefficients matches the exponents. I'm going to use the word molecularity to make sure we're clear there. Thank you. Okay. So the rate determining step molecularity matches the rate law order or orders, something like that. Okay. So those are the two criterion that we look at for matching mechanisms. And then we kind of just talked about this already. Catalysts are not consumed. They could potentially be yielded in such a way that they don't survive. So a lot of times catalysts are reused unless they're kind of damaged, and they can be damaged by unwanted side reactions. And then we talked about in thermochemistry path independent. So we just looked at the change overall. Like we didn't care what happened between. We cared about the beginning, the end, the products minus reactants, and that was what we kind of did. So with our thermodynamics path independent, that's what we did. H of reaction was determined by H products minus H reactants. We did not care about the path taken, but in kinetics we do care about the path taken, which is why we're talking about the mechanism of the process. Okay? And then we talked about this a little bit yesterday too, but when a catalyst is added, it speeds up the process. So it seems that if energy is changing, because it might get really hot, really cold very quick, but it doesn't change the actual energy release. It just makes it appear as if it's occurring at a faster rate, so we notice it's more noticeable. Good here? All right, so I think that now I'm going to check multiple choice. Yes, okay. So before I check multiple choice, turn and talk to the person next to you. I want you to check everyone who maybe starred or question mark next and talk first. Let's take maybe 3 to 5 minutes to talk. I think you guys can do 45 seconds before you talk to September.
How do you find the rate law? You do this with tracking you get the first
Somebody told me I copied them already. Somebody told me I had copied them before you could hack it initially. Can you look through your binder?
I don't know how to get the rate law. Like if I gave you one, yeah, I can ask you right here. So the rate law is based on the slower step, which is based on this. There's a contribution to because you didn't get this always but for this, like say we have this that is different for rate law, but otherwise it would be so one A. You're never gonna have if it was like 3A, it would be like A third order, B first order. And you only do the reaction. You only do the whatever the letter is, and whatever the coefficient is, the really one is that one. So I'm trapped at uni. I can't.
You can't.
But the rate changes. For sure.
All right, so let's go ahead and check these. Grab a separate color or a different color pen or something that will help you identify, like when you go back and study. If you need a highlighter or something like that, let me know. Anybody need a colorful writing device? I'm ready to throw them. Emily, Megan. Oh, Megan, that was a good catch. Niall, I like that one. Good catch, Niall. Good catch. Anybody else? Okay, so here we go. The units that I will work out some at the end, okay, but let's just check all the answers first. We'll work out the ones we need. 1A, 2E, 3D, 4A, 5B, 6C, 7A, 8C, 9E, 10D, 11C, 12B, 13B, 14B, 15B, 16E, 17A, 18B, 19D, 20A, 23E, I mean, my bad, 21E, you know, it's good numbers. Okay, so 21 is E, 22, the best answer is A, probably most people chose C, right? I would accept C. I'll tell you the caveat on that in a second, okay? 23 is E, 24 E, 25 C, 26 E, 27 B, 28 B, 29 B, 30 D, 31 A. Count how many you got right out of 31. So, 30 out of 31 is top of your paper. 8 out of 31 is top of your paper. Determine what you got first, and then we'll talk. I know you're. Which one? Yeah. 14. B, as in boy. All right, I'm going to take questions 1 through 10 first. Questions 1 through 10 first. 3. So the way that these are phrased, doubling the concentration of A and doubling the concentration of B will lead to a 4 times the rate increase. Basically, you can't, you're determining, based on how it's phrased, how the rate is impacted by these changes in concentration, your job is to figure out these orders. So the only thing those can be to make a 4 times fourfold increase in rate is that this has to be 1 and this has to be 1, because 2 to the first power times 2 to the first power is 4. So you're essentially just doing 2 times 2 times 2 is equal to 4. So that should be, which one was that one? Oh, D, right? Number 3 was D. Because it doesn't tell you that C is changing, so you're assuming that C is not really a variable to consider right now. It's just one of the reactions. Okay, continue, 1 through 10. 10? Okay, so it's first order with respect to D, and second order with respect to E. No change in overall rate. Okay, so not 0. So essentially, I'm going to have 1 times the rate at the end. Okay, so if I double D, it's raised to the first power, and I 1/4 E. Was this answer D? Yeah, okay. And I 1/4 E. Was it 1/4? Oh, sorry, this is to the... Oh, increasing this by 4, my bad. Okay. So if I multiply D concentration by 4, it's raised to the first power, and I 1/2 the concentration of E, that's raised to the second power. Essentially what I'm doing is 4 times 1 to the second and 2 to the second just means you're multiplying by 1/4. So the 4 and the 4 cancel each other out to make 4, which means the rate doesn't change by 8. It's still the same. Okay, how about through 15 now? 11. So in your Maxwell-Boltzmann and in your, Maxwell-Boltzmann, in all of these, when you change your temperature, it shifts the graph, but it does not change the area underneath. So C would be your best answer. I know the other one says total are the same for D and E, because of course gases will occupy different spaces at different temperatures. They spread out, so that's really not related to this graph at all. And then activation energy is the same, but more of them are meeting activation energy, but that's not what's happening in this graph. It's shifting to show more of meeting activation energy. So C would be best. Another through 15? Another? Okay, 14. For the rate law shown where the rate is measured in units of meters, okay, molar per second. The concentrations of X and Y are measured in molarity, which is the same as concentration, if you guys didn't know that. Which of the following are true? Okay, so we have rate is equal to K, X squared, and Y to the first. So this is molar per second. Actually, let's just solve for K. So, because basically you guys have to learn how to, yeah, what's up, JT? Okay. So you guys have to rearrange equations or just look at these and determine how you can write K units to make this equal the molar per second. I'm actually going to do that first. If this is molarity and it's squared, and this is molarity, and it's to the first power, and I only want one molarity on top of the end, what has to be in the denominator of K? M squared, right? Because I only want one of these at the end, so this has to cancel. So I know it has to be molarity squared in the denominator. And notice there's no time over here, so therefore I also have to have time in the denominator as well. So K is units is per molar squared seconds. How do I rewrite that, including liters and moles, those separately? Liters squared, I heard, over moles squared per second, right? So this is the same as this, just making sure we're clear on how to determine that, okay? So the units of K are not molar squared per second, and you need Q to be molar to -2. Doubling the concentration of Y while keeping the other will not affect the rate. Certainly it will affect the rate just to the first power. Overall, it's to the third order because 2 plus 1 is 3. Okay, so that 14 is just the nature of how you have to find the units, and I think that was probably the harder part on that one. All right, through 20? Yeah, 15. 15? Okay, so actually I'm just going to word right here. So given this rate law, your job is to make a 16-fold increase on the rate. The only way you're going to do that is by looking at each question and just manipulating the variables of concentration to see how that impacts the rate. So for this answer in particular, you double the rate, or sorry, double the concentration of Q. Doubling that concentration actually means it's going to increase the rate by 4. By doing the same thing to R, doubling its concentration raised to the second power will increase the rate by 4, but collectively 4 times 4 is 16, so it will 16-fold increase the rate. Okay, another one through 20, Megan? 17? Yes, yes. So for 17, if you had to write your own rate law, the rate is going to be correlating with the rate determining step. So you could, if there was an answer choice, you could have had K, concentration of F, concentration of A. But that wasn't an answer, so you had to manipulate it based on the fast equilibrium that was occurring first. So what did we substitute in for F? A and B, because of the fast equilibrium that was occurring. So instead of that, because of the answer choices given, we had A, B, and A, but we can't write those all separately. We're going to combine those A's to make A squared. So that's why we had to choose A here. No, you can include catalyst. If there's a catalyst at the rate determining step, if it is a part of the reactant, so it would be a part of the rate law. Okay. All right, keep going. Through 20, 19, 19. So if you ever have 1 over concentration, what order is that? Second, so then we narrowed it down to D and E. So this is memorization. Slope is positive, K. So that's just a memorization of integrated rate law. All right, through 31. All right, 21 and 26, right? Okay, 21, 25, 26. Okay, so 21, you've got this reaction mechanism given. Step 1 is the slow step. So since you already know step 1 is a slow step, you know that because it says step 1 is found to be the slow step of the reaction or mechanism. You already know the rate law is K Rx. That's it, right? Because that's the only reactant in that slow step to the first power, by the way. So when you're looking at these, the reaction will be found to be first order with respect to Rx. Check, because that was what the rate law said it was. Reactant intermediate, that's expressed by this cation. Yes, because it cancels out. And it's independent of the concentration of hydroxide. The rate technically is, because hydroxide is not in the rate determining step. So it's independent of that because it's not controlling the rate. It's a part of the mechanism, but it's not controlling the overall rate. Yeah. Nope. So if we don't care about products really, period. The only thing that controls our rate are the reactants. So if hydroxide were in the rate determining step as reactants, it would be dependent upon that, but it's not here.
So if it was in the product,
so if OH were in the products of either of those, it still would not be true, right? Because it's independent of that, because it has to be in the reactants of the rate determining step to be controlling the rate. Okay, 25, 24. Okay, so looking at this table, and so this is what I would expect. Do you notice that it says like use the table for the following 2 questions? You have chunks of questions like that That's what they're leaning more towards on the AP exam, so I try to mimic, and you guys have seen that before in your test, like, use this graph for the next 3 questions, or use this table for the next 3 questions. So, even if you get stuck on one question, you can get, like, maybe the 2 others, you know what I'm saying? So don't get stuck on one and be stuck there for 5 minutes. Okay, so from trial 1 to trial 2, it looks like W was multiplied by 2, X was staying the same, and Y was staying the same. And the rate did what? It didn't change, right? So it was just basically multiplied by 1. So this W has to be to the 0 power, because it's the only way you're going to get a rate to not change when you change this concentration. So W to the 0, or to the 0 order. From trial 2 to 4, 2 to 4, W is not changing, X is not changing, and Y is, I'm going to go the other way because it's going from 0.001 to 0.0005. So if I think about it going up, it's being multiplied by 2 from trials 4 to 2. The rate was therefore multiplied by what? What? You say 12 or 4? 4. I thought somebody said 12. Like, whew. Okay. So 2 raised to what power gives you 4? 2. So this is Y to the second power. And then X, once you determine what's staying constant here? 1 and 3, thank you. For 1 and 3, W stayed constant, Y stayed constant, and then X multiplied by 3. The rate, as you see it there now, is multiplied by 3, so X must be to the first order. Okay, so it just takes a minute of table logic. Okay, now 25. Everybody look at that reaction. I know you have it right in front of you. 2W plus 3X plus Y yields Z. If you have something like this, and if you read the table, it tells you the rate as a production of Z, right? So then the question to you about X, you just look at the relationship between Z and X. So for experiment 1, production of Z was 2.1 times 10 to the negative 4th molarity per second. So the relationship between Z and X is a 1 to 3 ratio. So what you're going to do is multiply by 3 X's are consumed for every 1 Z produced. So we're just going to multiply the rate by 3 because it's being consumed at 3 times the rate as the production of Z. So that would be 6.3. And why is it not D? You can't have a negative rate, okay? It doesn't matter. The consumption where it tells you about like the consumption, the decreasing nature of it, you don't need a negative on that. 27, is that what I heard? Yeah? Okay. Tripling the concentration of a single reactant R in a multi-reactant reaction leads to a 9-fold increase in rate. Can we deduct that? Okay, so if we triple the concentration of something, it's raised to some order. It causes the rate to increase by 9 times. Essentially, we're just pulling these two pieces together to say 3 to the X is 9. So then what's X? 2. So 3 times 3 is equal to 9. So that has to be an order of 2. And then what's the rate loss? So if you're looking at the slow step is NO2 plus NO2. So it has to be NO2 squared because there's 2 of them. So it's matching the molecularity for that slow step. All right, let me pause. I will take more individual questions on this after. We got to switch over to FRQs, okay? So I know I saw some of you guys had it out for me. Thank you. Your 1, 2, and 5. I would like to try to check those today in class. So I'm going to give you guys maybe about 20 minutes or less to finish up FRQs. Okay? So if you need to spread out work, try to finish up all of them. If you don't finish, you'll finish for homework tonight. But specifically, I want my 1, 3, and 5 teams. Raise your hand if you were FRQ 1. Okay, 2s. I got 2 people there, 2? Oh, 3, okay. 5. Okay, I'd love for you guys to be able to present today. I think it would be too much for tomorrow. We present 7 FRQs tomorrow. Okay, so work. You're responsible for all 1 through 7, but you're just presenting one of them.
How do you want me to go about
I'll have you, I think you were 3, but I think, were you my last one? Okay, then you're gonna be 4. You'll be an FRQ 4 group, which is presenting tomorrow. It's just make sure that you're like solid in that FRQ. You should be solid in all of them, but make sure you're able to verbalize what you feel. Okay. Okay. You don't have to work in your group right now. I'm just wanting you to know that your group will be presenting together. So finish up all your FRQs right now.
So it's 4, like, so is there another group behind it, or is it just?
There's like 2 people in your group, so you guys will just be presenting work tomorrow.
It's up to you. If you need to challenge your brain to pull that information, but if you don't have it, then listen.
Are you doing it for time? I gotta start. No, we don't have to work in our groups. I'll work on it since I have some questions. So wait, do you have a separate group? I had a headache yesterday.
this concentration that will what happened was we figured out that this deadline concentration
They would like to see us for the actual part, maybe they want to go. This is saying, Guys, focus. I'm coming around. Please don't let your hand be up neglect from your work. So I'm one person. You just gotta wait. Yep.
I said yes, we had this little increase. This side.
Where's that man with my little boy? Yeah, it's not working.
So, now that you know that this is first order, you'll figure out what it is. That's not how it's holding it. I already picked one.
So it's to the one pallet. To the one pallet. It's smart, one pallet. I'll explain. I'll explain it. I got it. So then what changed to 6? This is 6, and this is 2. So this is changed by 12, so 6 times 12. So this is changed by 2. Now this is changed by 2. This is the first time I'm showing this now. This wasn't changing. So time 6. So I said it in the reaction, during the reaction,
Okay, so it includes an experiment creating the initial rate of formation. And then you multiply by the BC, so you multiply this by 2. So you're gonna the rate of formation by 2. Never any knows that I would no, and then I say it's the evidence. When someone answers my question, I'll just text like some things you can but like
All right, group 1, FRQ 1, raise your hand. All right, you guys almost ready? You guys want me to talk real fast because I want this to be fluid and not like, okay. FRQ 2 and 5, you're coming next, okay? So if you're in FRQ 1, 2, or 5, go ahead and group your people and talk about what you gotta talk about. Yeah, most of us are 2 or 3 or 4. Cool. Number 5. What'd you work for A?
So you basically take the natural one off of the line, take one of the sample off of the exceptions, then you obtain the linear regression equation. From there, you just to take the new value, subtract it from your